In this video, we're going to see an algorithmic technique called divide and conquer. Divide and conquer can lead to some very beautiful and simple algorithms and is a great tool to have in your toolbox. I'm going to introduce divide and conquer with a relatively simple example. In the next videos, we will see how to apply divide and conquer to design sorting algorithms. So we'll see the algorithms that use this paradigm like merge sort and quick sort. I'm going to introduce divide and conquer by means of this example. This is a Leetcode problem called Best Time to Buy and Sell Stock. It's rated easy on Leetcode, and it's also on the Blind 75 list of problems. So here's the problem. We're given a vector prices of size n, where prices of I is the price of a stock on day I. At some point we can buy the stock, and then at a later date we can sell it. So note that we have to buy it before we can sell it. And we can also buy at most once and sell at most once. The question is, what is the maximum profit? So this is kind of a wordy definition. If you prefer a more mathematical definition, what we want to compute is the maximum over I less than j of prices of j minus prices of I. Right, so how this corresponds to the word definition, I is the time where you buy, j is the time where you sell. You have to buy before you sell, so I is less than j. And the profit is the price when you sell minus the price when you bought. So prices of j minus prices of I. Okay, so that's the problem. Let's look at some examples just to make sure that we understand the problem. So first, say that the price at day 0 is 9 and the price at day 1 is 2. Okay, so in this case, the maximum profit is just 0, right? We just don't buy or sell anything. The only other option would be to buy on day 0 and sell on day 1, but then we'd lose money. Okay, so we don't want that. It's better just to do nothing and have profit of 0. And I like this example because it shows that the answer is not just the maximum entry of the array minus the minimum entry of the array, right? The ordering between the entries is critical, and that's kind of what makes the problem interesting. So here's another example. This example is harder to see immediately, but the maximum profit in this case turns out to be 6. Okay, so you can just pause the video if you like and think about why that's the case. It turns out that the best thing to do is to buy on day 4 at price 2 and sell on day 6 at price 8. And this is the example that we're going to work through when we design our algorithm. Okay, so let's design a divide and conquer algorithm for this best time to buy and sell stock problem. So you might come up with a different algorithm to solve this problem if you think about it yourself. In fact, for this problem, the divide and conquer approach is not optimal. There is a faster algorithm. But I think this problem is still a great example to illustrate the divide and conquer principle. Okay, so here's the idea. There are 3 possible cases for when the best time to buy and sell can occur. The best time to buy and sell could both occur in the first half of the array, or they could both occur in the second half of the array. And the remaining case is that the best time to buy occurs in the first half of the array, and the best time to sell occurs in the second half of the array. Okay, so if you think about it a little bit, you see that these 3 cases are exhaustive. Right? It has to be one of these 3 cases. So let's look more in depth at these 3 cases. The first 2 cases are exactly instances of the buy and sell stock problem, the same problem that we started with, but on an array of half the size. So this is the divide part of divide and conquer. We express the original problem in terms of instances of the same original problem, but on smaller inputs. Usually in divide and conquer, there is some extra work that needs to be done in addition to solving the subproblems. in our example, this extra work arises because of the third possibility, that the best time to buy occurs in the first half of the array and the best time to sell occurs in the second half. But this is actually an easier version of the original problem because this extra information, it already takes care of the ordering for us, right? That we have to buy before we have to sell. It's kind of guaranteed by the third case because we know that we're buying sometime in the first half and selling sometime in the second half. We're automatically assured that we buy before we sell. So do you see how to solve this case? Well, the best time to buy in the first half is when the price is lowest. So it's the minimum value in the first half. And the best time to sell in the second half is when the price is highest. So it's the maximum value in the second half. Okay, so all we have to do for the third case is compute the minimum value in the first half and compute the maximum value in the second half. And we can do this in time theta of n. And we know how to compute the minimum and the maximum. So let's work through the algorithm on our example. The maximum achievable profit is going to be the maximum of the maximum achievable profit in our three cases. So again, in this case, that's going to be the maximum profit we can achieve on the first half of the array, the maximum profit we can achieve on the second half of the array, and the maximum profit when we buy in the first half and sell in the second half. In this case, we can directly solve. We see that the minimum value in the first half is 3, the maximum value in the second half is 8. So the maximum profit in this case is 5. So the third case we can directly solve, and the first two cases we're going to solve recursively. Okay, so let's see how to do that. On the first case, we want to compute the maximum profit now on the first half of the array, and we solve this recursively. So again, this is going to be the maximum profit from the three cases. The maximum profit from the first half of the array. And just so the example does not get too long, I'm going to stop the recursion here when we get to instances of size 2. So when the size is 2, we can directly see in this case that the maximum profit is 2. Right? Basically, our only two options are do nothing or buy on day 0, sell on day 1. Okay, so the maximum of those two cases here gives us profit 2. The second case is the maximum profit on the second half of the array. The second half of the array is 9 and 3. So in this case, we just do nothing. The profit is 0. And the third case where we buy in the first half and sell in the second half. So the best thing for us to do here is buy when the price is 4, sell when the price is 9, which gives us a profit of 5. Okay, so the maximum of these three cases is 5. So that's the maximum profit we can achieve on the first half of the array. So now we go to the second case, the maximum profit on the second half of the original array, which has values 2, 5, 8, and 1. And we again recursively apply the same algorithm. So the maximum profit is going to be the maximum of our three cases. So the maximum profit from the first half, which is 3, the maximum profit from the second half, which is 0, and the maximum profit when we buy in the first half and sell in the second half. And in this case, we can achieve profit 6 by buying when the price is 2 and selling when the price is 8. So the maximum of these three cases is 6. It's actually achieved in this third case when we buy in the first half and sell in the second half. Okay, so now we've recursively computed the maximum profit in the first case, the maximum profit in the second case, and we directly computed the maximum profit in the third case. And the answer is just the maximum of these three cases. So in this case, the answer is 6. Okay, so that's the example. Here's the algorithm expressed in code. And a nice thing about divide and conquer algorithms, when you express them recursively, you can get this really short and simple code. Okay, so we have a function here called max profit, and it takes 2 iterators. And so the intent of this function is that we compute the maximum profit achievable on the portion of the vector that starts at begin and goes up to but does not include end. Okay, so this is the usual way we reference an interval in C++. This is a half-closed interval. So like any recursive algorithm, we need to have a base case. So that's the first couple lines of the code there. If the distance between begin and end is at most 1, then we can just return 0, right? If there's only 1 price or 0 prices, then we can't buy and sell. So the answer is just 0. So that's the base case. And again, you can find this code up on Godbolt. After the if statement, then we create our subproblems. So in this case, to create the subproblems, all we have to do is compute the midpoint between begin and end. So that's what's done in that step there. So we saw very similar code to this in binary search, right? Okay, and then we can directly compute the maximum profit achievable in case 3, where we buy the stock in the first half and sell in the second half. So I'm just using some library functions here called max element and min element. They're in the algorithm library. So we can just do this step in one line using these library functions. So so we just compute the maximum element in the second half and the minimum element in the first half, and we subtract these. And that's the maximum profit from case 3. And the final line of the algorithm, we return the maximum of the 3 cases. So the maximum profit on the first half of the vector, which is computed by the recursive call to max profit from begin to mid. The maximum profit on the second half of the vector, which is computed with the recursive call to max profit with arguments mid and end. And by first half, this variable by first half sell second half, which is the maximum profit from case 3. And that's the whole algorithm.